Let's talk about acid-base reactions. Acids and bases are some of the most important electrolytes. You deal with these on a daily basis. They can cause color changes in certain dyes called acid-base indicators, so we take advantage of this sometimes with some weak species to determine the equivalence point or pH of a solution. Many household acids and bases are encountered every day. Red cabbage juice, that could be used as an acid-base indicator over the whole range of the pH scale. Vitamin C, that's ascorbic acid. Aspirin, salicylic acid. Milk of magnesia, base. Vinegar, acetic acid. There are many different ways to define acids and bases. They all give you the same result, but for different reasons. We'll cover a couple of different acid-base definitions. They basically build upon each other. First one we cover is the Arrhenius concept. The Arrhenius concept defines acids as substances that produce hydrogen ions, also known as hydronium ions, when dissolved in water. Example is nitric acid, a molecular substance that dissolves in water to give H+ and nitrate ions. So written as a dissociation, you have nitric acid in water breaks up into H+ and NO3-. As I mentioned earlier, we also refer to H+ as hydronium ions, so we could write this as an ionization process as well, which have nitric acid reacting with water to form hydronium ions and NO3- nitrate ions. Notice, you will encounter acid ionization equations written both ways, either as a dissociation or an ionization. You need to be familiar with both ways. That H+ and H3O+, that hydronium ion, is used interchangeably. The Arrhenius concept defines bases as substances that produce hydroxide ions when dissolved in water. An example is sodium hydroxide, an ionic substance that dissolves in water to give sodium ions and hydroxide ions. So you get sodium hydroxide breaking up to form sodium ions and hydroxide ions. By Arrhenius concept, is ammonia an acid or a base? Well, if you write your reaction, get ammonia plus water, forms ammonia ions and hydroxide ions. Well, by definition of Arrhenius, if it produces OH-, it's a base. So in this case, ammonia is a base. By Arrhenius concept, ammonia produces hydroxide ions, therefore it is a base. However, this concept does not cover all acid bases that exist, which gives us a more useful acid-base concept, especially when dealing with aqueous solutions, which is the Brønsted-Lowry concept. The Brønsted-Lowry concept of acids and bases involves the transfer of protons from acid to a base. In this view, acid-base reactions are considered proton transfer reactions. The Brønsted-Lowry concept defines an acid as a species molecule ion that donates a proton to another species in the proton transfer reaction. So basically, acid is something that's giving up a proton. A base is defined as the species molecule ion that accepts a proton in a proton transfer reaction. So an acid donates a proton, a base accepts a proton. Let's go back to that original example we did with the Arrhenius definition, where we said ammonia was a base because it was giving up OH-. Let's look at the Brønsted-Lowry concept and see if we come up with the same conclusion. We see in this reaction that a hydrogen is coming from a water molecule to the NH3. You can see that because on the product side, we see that H2O is now OH-. It has lost a proton. And we see that NH3 is now NH4+. It gained a proton, H+. So by Brønsted-Lowry definition, since ammonia is gaining a proton, it is a base. And in this case, water is the acid because it is giving up the proton. The water molecule is an acid because it donates a proton. the ammonia molecule is a base because it accepts a proton. Using Brønsted-Lowry concept makes it easy to write acid-base reactions. You remove a proton off the acid component and place it on the base component, giving you the products. Water is amphiprotic, meaning it can act as an acid or base. Since ammonia is the better base, water is the acid in this case. We know the bases and we know the acids in water, so we know water will be the opposite. If we know something's an acid, water is going to be a base. If you know something's a base in water, then water is going to be the acid in your Brønsted-Lowry concept. So it's simple to write a reaction. When you have an acid base, you know the base is going to accept it. So in this particular example, we know that a proton went from water to ammonia, which gives us NH4+, and then you lost the proton, so that left you OH- on the product side. We attained the same conclusion that ammonia is a base using this theory. However, we didn't look at the production of OH- to make the decision. It was based on ammonia accepting a proton in the aqueous solution. If you learn the acids and bases in water, it will inform you how water reacts in the reaction. We know that nitric acid is an acid in water, therefore water must be a base in a proton acceptor reaction. So if I have nitric acid plus water, I know that nitric acid is an acid in water, so that means that it's going to donate a proton to the water, which means it would give me H3O+, the hydronium ion, and leave me NO3-. So you have that proton that's being donated from nitric acid to water. So nitric acid is an acid, proton donor, and water is a base, proton acceptor. The consequence of a Brønsted-Lowry concept is that on the product side of the acid-base reactions, they are also acid-base products. This leads us to the term of conjugate acid-base pairs. These are species that differ by a proton, with the species containing more protons being the acid. So in our example up above, we know that HNO3 is an acid. The conjugate base on the other side is NO3-. And we know that H2O is a base. Its conjugate acid on the other side is HO3+. Other examples. HCN is an acid. The conjugate base of that, if it donated a proton, would be Cn-. Talked about hydronium ion. The conjugate base of that is water. If I have H2SO4, the conjugate base, if it gave up a proton, would be HSO4-. H2PO3-, if it gave up a proton, would be HPO3-2-. That's a conjugate acid-base pair. In summary, the Arrhenius concept: acid is a proton producer, base is a hydroxide ion producer. Brønsted-Lowry: acid is a proton donor, a base is a proton acceptor. Homework 28.